guys, so welcome back to another day of organic chemistry together. So today what we're going to do is take the 3D work that we did yesterday with wedges and dashes and kind of introduce another way of showing molecules in 3D, okay? And so the convention that we'll use to show the 3D today is known as a Newman projection. And so our two learning targets are being able to represent molecules using a Newman projection, and then we're going to be comparing something called torsional strain between two of the different conformations that we can generate. And so for the most part, I'll just be kind of reading a lot of the text to you. We'll kind of look at some different video images on the side, on the left here, since we can't be together and actually consider the molecules in 3D, kind of building a kit. All right, so first of all, kind of just a reminder about the wedge and dash convention, kind of over here on the side. And so what we learned yesterday is that the wedges, they represent bonds that are coming out of the page toward us, and the dashes represent bonds that are going into the page or kind of away from us. And so if you look here at the little video on the left, thanks to, again, masterorganicchemistry.com, kind of for these resources, and you'll notice he's got the tetrahedral built and he's kind of rotating it back and forth, and you'll see the little wedge and dash notation. So here that front bond is sticking out, now it's going back, kind of so on and so forth as to what we see, in the molecule. And so today what we're going to do is kind of introduce three other projections that can be used to show 3D structure on 2D paper. And so they're useful for showing what we call conformations of molecules. And all a conformation is it's just different orientations of the molecules that you can obtain by rotating the molecule around a bond. And so within a molecule, single bonds typically have free rotation. And so what you can do is take one of those bonds and rotate around it to kind of generate different conformations or different options for the molecule. And so I've got that in the video now. See how he's kind of twisting one of the groups to kind of rotate around that single bond. And it's putting the hydrogens kind of in different orientations with respect to that front carbon that's staying in place. All right, so kind of minimize this for a second, pull this one up. So the sawhorse projection is kind of one option, and it kind of gives you a view of the molecule from the side. And from this view, you can kind of see how different groups may rotate, about the bond. So it gives you a good, long, kind of extended single bond there. The Newman projection, which is kind of our focus today, gives you a front view of the molecule as if you're staring straight down kind of one of the carbon-to-carbon bonds. And it shows also, like a sawhorse, how the groups can rotate about a single bond, but it also gives you a better picture of how those groups will interact with other groups that kind of end up in the same areas, okay? Then finally, there's a Fisher projection, and this is kind of a top side view of the molecule, as if you're kind of above the molecule and looking straight down on it. And typically this is less frequently used than the other two projections, but especially if you do like biochemistry or biology applications, this is used really frequently when talking about sugar molecules. So that's one place where you'll see the Fisher projection be in use. And so, all right, so now on to the Newman projection. So it says to draw a Newman projection, first pick a carbon-to-carbon bond and then rotate the molecule so that you are looking straight down the bond. Closest to you, you will see a carbon atom with three other bonds coming from it, kind of like points on a triangle. And so you draw the view by making the carbon in the front a circle that, quote, blocks the carbon on the back of the bond. And so I'm going to scroll down kind of here. And so what we mean by kind of rotate the molecule towards yourself, if you'll notice, as he's picking up kind of this molecule, he's turning it so that that front carbon is directly facing him. And so what we're going to do is look directly along that bond. And so what you'll see is kind of once he turns it one more time, you have kind of all of the hydrogens kind of blocking the other hydrogens in the bag. It's almost as if they look like they're on top of each other. And so if we look at kind of the pictures of that in our notes here, this is kind of the ball and stick model again. And so we're looking down, kind of this carbon to carbon bond. And so our eye is going to be looking, kind of straight ahead here. And so what we see from that view is we see kind of 3 hydrogens are attached to each carbon. And so the front carbon we're going to represent with a circle, and then we draw kind of 3 points coming off of it, and we'll add on the groups, which in this case tend to be hydrogens. Then the back carbon, we'll draw in groups for it. Now technically the back carbon's hydrogens kind of line up, directly with the front carbons. But to show them, we're going to come to the side just a little bit, but we technically know that the hydrogens line up. We just have to come to the side a little bit to show them. And so the name of this kind of orientation is called an eclipsed conformation, all right? And so just like when you have eclipses, like where the sun and moon might, kind of cover each other for a period of time, the hydrogens are eclipsing or overlapping with each other. Now, what if we take that front carbon and we rotate it so that the hydrogens are no longer eclipsed, but they're alternating? And so again, we'll represent that first carbon with a circle. And in this case, what we have is we have a hydrogen kind of out to the side, hydrogen out to the side, and a hydrogen down to the bottom. So these are these 3 hydrogens right here. Then for our back carbon, it also has 3 hydrogens. One is kind of sticking up, and the other 2 are kind of sticking down into the left and down into the right. And so where the hydrogens are kind of alternating, this is what we call a staggered conformation. All right. So we have the main conformations being eclipsed, where kind of the bonds overlap, and then the staggered conformation where they kind of alternate. Okay. And so one of the benefits of using the Newman projection is that it allows us to see how the front and back groups relate to each other spatially, right? So it's kind of like how close are they in 3D space? And so this is going to lead us to something that's called the dihedral angle, or sometimes it's called the torsion angle, all right? And so the way you kind of track the dihedral angle is you're still looking along kind of that middle bond, and the angle is going to be between groups A and D when you're looking kind of directly along that main bond of the molecule. And so when we turn the molecule around and look at it via a Newman projection, it's kind of groups A and D that are here close to each other. Now, if it's an eclipsed conformation, where you have the hydrogens kind of directly, on top of each other, the dihedral angle will be 0, okay? But let's say, on the other hand, that you turn it so that you're in a staggered conformation and you're looking from D to A. So that would be like examining the angle between this top hydrogen and this bottom hydrogen here. So if we're looking at the angle kind of between those 2 groups, it has a dihedral angle of 180 degrees. It's as if we've gone kind of halfway around a circle being 360 degrees, okay? And so how you rotate the bond kind of determines, what angles you generate. So here, when you're eclipsed, we have a 0 degree angle between these 2 hydrogens. As you rotate that back CH3 group and keep this front carbon still, what you can generate is the different angles. You can expand it to 60 degrees, 120 degrees, 180 degrees, kind of so on and so forth, all the way until you get back to the 360 degrees, which would be another eclipsed conformation. And so we may ask, are all of these different orientations kind of equal in energy? And the answer to that is no. So what happens when you have an eclipsed conformation, where kind of all the groups line up and overlap, it introduces something that's called torsional strain. And so typically, the further apart the groups are in space, the better it is, because they're not as kind of clumped together, and it doesn't create as much strain on the molecule. So your eclipsed conformations tend to have more strain due to the substituents on those carbons, the hydrogens, being kind of really tight and, relatively close together, kind of within the same space. And so there's kind of a famous graph that normally your organic chemistry teacher will introduce kind of at this point. This is kind of a simplified version of the graph. But what we see is that the staggered conformations, where the groups are spread out, they lower the strain on the molecule. And as a result, that kind of lowers the molecule's overall energy and makes it more stable. So as we track the graph, the eclipsed conformations are at a higher energy, the staggered conformations at a lower. And as you keep rotating that bond, it kind of passes through eclipsed to staggered, eclipsed to staggered, eclipsed to staggered. And that generates kind of different levels of strain, which overall affects the molecule's relative energy. And so just kind of a good general rule for you to come away with is eclipsed conformations put the groups kind of more on top of each other. That creates more strain, which lowers the stability of the molecule and raises its overall energy. And so right quick, I'm going to take you back to the website and pull up one of the videos kind of bigger for you here. This way you can see it a little better. So here's another kind of staggered conformation there. So I'll let him pull that one up one more time. All right. And then let me keep scrolling down. Right quick. Here's what I wanted you to see. So what they're going to do is, just like we were talking about on the notes, how you can rotate this hydrogen bond kind of around on the back carbon if you hold the front carbon still, and you can generate these different angles and pass back and forth between eclipsed and staggered. And I wanted you to see that kind of in 3D. So notice this front carbon is staying still, and he's going to rotate that back carbon, and he'll kind of show you the little drawing here in the top right corner. So we've got eclipsed, staggered, eclipsed, staggered, and then back to eclipsed. And if you want to spend some more time kind of looking at these particular videos that are a really good resource, I put the Master Organic Chemistry site link kind of onto the top of your notes, and you can check it out there. All right, so that's all for today. Good luck on the practice problems, and again, just let me know if you need anything. Thanks for watching.